Welcome back, folks. I'm going to introduce some of the values and variables we're going to use over the course of the semester. You've probably heard these before. Okay, if you've taken your prereqs, you certainly have. I want to make sure we're talking the same language. There's people are coming from a lot of different backgrounds in this class, and I want to make sure that we're using the same variables, we're talking about them the same way. I kind of want to highlight some things that are important as the semester goes on that maybe you didn't pay attention to in those prereqs. I think it's worth us taking a little bit of time to do this. So I'm going to start out in this video. I'm going to chunk them out into as small videos as I can, and we're going to start out talking about charge and current. Charge is pretty important. It's really the fundamental. It's really the fundamental thing that we're interested in as we begin analyzing circuits. So it's going to be the first thing that we talk about. And anything that we do with electricity and electronics, we're really dealing with charge, and we're using that charge to do one of two things. We're having that charge do work for us, or we're having charge convey information. Okay, so if I want to spin a motor and automate something that might ease the physical labor that a human has to do, we're doing some work. Okay, so motors are the easiest thing to point to in that case, and conveying information. We're using electrons right now so that I can be in your living room or wherever you are listening to this, and we're moving some electrons so that you can see this pretty face and anything that I write up here. Okay, so we're doing work or we're conveying information. We're going to do that with charge. We do this by pushing electrons. Okay, maybe an oversimplification, but we're pushing electrons around. Okay, and we're going to measure charge in coulombs. Okay, measured in coulombs. Okay, and we get a capital C for that because it's named after an old dead guy. There's a lot of them going around this class. So we're going to measure charge in coulombs, and if we're pushing electrons around, then we might say, hey, what's the charge of a single electron? And it's not very big. Okay. This isn't a number that you necessarily need to walk around with in your head. It's a simple search away. If you need it, it's usually in reference material, but it's stuck in my head whether I need it or not. 1.602 E negative 19 coulombs. Okay, and I'm going to say that that's a scientist number. That's something a physicist would throw out there, and I can tell immediately because it's not an engineering notation. Okay, it's not an engineering notation. Well, it looks like I have one digit to the left of the decimal point. That's okay. But 19 is not a multiple of 3. It's also really tiny. Okay, so this is one electron. If I want to get 1 coulomb, I'm going to need a lot of electrons. Okay, so how would we do that? We would, well, first let's make this, let's put this in engineering notation. So if I slide the decimal point over 2 to the right, then I can rewrite this as 160.2 E negative 21 coulombs. Okay, and if you're looking at your SI prefixes, this might not have been in the table in the last video because 21 is pretty small, but we could just as correctly write that as 160.2 lowercase z capital C. That's zeptocoulombs. Okay, so 1 electron is 160.2 zeptocoulombs. It's pretty small. We need a lot of electrons to make 1 coulomb. Okay, so we're not really likely to see individual small values of charge talked about in coulombs. We're more likely to see some of our SI prefixes come out here. So picocoulombs, nanocoulombs, microcoulombs. And if you're talking about a single electron, it's a zeptocoulomb. Okay, that's a pretty... we don't get down that small very often. Okay, so charge is a lot more complicated than that, I promise you, and certainly it was in your physics courses. But this is our starting point. Okay, we want to move this stuff around, and if we're going to talk about it, we're going to, let's get a different color here and say charge. Okay, the unit for charge is coulombs. Okay, capital C when we abbreviate it, and the variable we use for charge is capital Q. That's going to be a constant value of charge, or lowercase q if it's a time variant value of charge. And we'll talk about both. You'll see both in some of your problems. So that's our starting point. Okay, now charge by itself, at least to me, there's certainly some physics problems that might disagree with what I'm about to say. Charge, just sitting there doing nothing, isn't that interesting, at least to me. As we begin analyzing how circuits behave, we want to know how charge is moving. Because if we want to do work and we want to convey information, we have to take charge and we have to move it from one place to the other. In order to talk about charge moving, then we're going to talk about our next value and variable, and that is current. Okay, and this is really just the flow rate of charge. So if you want to think of it as flow rate, I get a lot of MEs on these, watching these, I know that, and so it's flow rate. So if you want to talk about cubic meters per second or something along those lines, if you're moving a fluid, it's the same idea, but we're moving little bits of charge. And if we're moving little bits of charge, then we can state it this way. So if we have, we're going to use the variable I, okay? You got to speak more French if you want to understand why that's I. That's okay too. Okay, if we're talking about fixed quantities, you may see it stated this way, delta Q over delta T. Okay, so Q is charge from up here. Lowercase t is time. Okay, it's always going to be time. And if I take some change in charge over some change in time, and I divide the time into charge, then I'm going to get a value for the current. Okay, that's if everything's constant and nice and pretty. But more often than not, we're talking about a time variant current, and that's going to take a similar form, but we're going to have the time derivative of charge, okay, and that's going to be a time variant charge. So if we have a function that represents the charge in a particular point in the circuit, then we can take the time derivative and we can find the current flowing through that part of the circuit. Okay, so we may see it stated both ways as we work our problems. If we're working with a function, we're going to take the time derivative. If we're working with fixed values, this form is just fine as well. And we can kind of swap back and forth between them. Hopefully you can see we got dq over dt over here, and we got delta q over delta t down there. So they're certainly related. Okay, so but if we're talking about derivatives, we can flip it around a little bit, and we can say, well, if I have the derivative form, I can also get the integral form. Okay, so if I want to figure out how much charge has moved in a circuit over some period of time, and I know the current as a time variant function. Okay, so I'm going to say we have to change our variable of integration, so we're going to use tau, and we start at some time t0, and we move to some time t, and we're integrating with respect to tau here, and we have some initial condition, of course. We may see it in that form. I try to state my problems using the derivative form. It's a little more compact. It's easier to work with. But if we want to take the inverse of this, we can just as easily move over here. Okay, a lot easier to take the inverse of this one to get charge. Okay, we just take the current and we multiply by the time. All right, so we may see it in those two forms, and I think you should see them and be aware of them. Okay, so summarizing this one, okay, and this one has a little bit of a wrinkle to it. If we want to talk about current, did I underline up there? Nope, current. Then we're going to deal with the unit. Okay, and the unit is another dead guy. Hopefully I'm not offending anybody with that. Ampere, okay. And he gets a capital A. A lot of times we call that, since we are a little sloppy with language, we call it an amp. Okay, so we just abbreviate it down to the word amp, which is fine. And you'll hear it. I'll say it, and most everybody I've worked with frequently calls it an amp. Now, here's the wrinkle. We know that an amp is charge over time. Okay, so when we're working some of the problems in this first section of the class, I want you to pay attention to your units, and the alternate unit for if I make any spelling errors, don't tell me. Okay, alternate unit is going to be the Coulomb per second. Okay, so we may see it written as Coulomb per second with a lowercase s. So if we know the time and we know the charge and we want to find the current, we can do that. Or if we know any of the two, we can rearrange it and find the third. Okay, what's really going on here is, I'm going to draw you a picture. Stand back. I know I've got this fancy pen here. Well, we'll stick with blue. Okay, if we have some wire, you like my wire? Okay, and we take a cross section that's supposed to connect, and we count how many, the charge of the electrons passing through this cross section. That's how fancy I'll get for drawing. Okay, get a little bit of perspective in there. Okay, so if 1 Coulomb passes through this cross section of wire in 1 second, then that's 1 ampere, okay, or 1 amp. So that's current. It's the measure of charge flowing through something. All right, and that's our flow rate. All right, so those are our first two values and the variables that we use with them. Go back out. I'll ask you a couple really small questions, really just get you moving with the formulas and hopefully working with your calculators, whatever tool you're going to use to do calculations. That's what I suggest you use to answer these problems. And give those a try, and then look for the next video as we move on to the other values and variables that we'll use for the semester. All right, so stay tuned, and good luck.